In this video, we'll quickly talk about how training would work in more general conditional random field setup. We've mentioned in previous videos that we do not need to restrict ourselves to linear chain conditional random fields. If we were modeling a pixel labeling problem, we could use a grid structure where each node would correspond to one of the pixels in the image, and we'd have factors that would express preferences on the joint value of neighboring pixels in the image. Or we could have a very complicated structure over a graph where we have several types of loops, and we could even have factors that would involve more than just two variables. We could even have a structure that varies for different pairs of training inputs and targets. So I'm mentioning here an example where we have web pages and we're modeling the label between web pages that share a link. And if we had different groups of web pages, then the different groups of web pages might have will of course have different network structures. So if I'm modeling the web pages from the pages of one in one university website versus another university website, of course these would be different pages and they'll be connected differently. So the conditional random field framework is very general for modeling the interaction between random variables, so concepts that we're trying to model. So now what about training such general conditional random fields? To do that, we'd still perform gradient descent. So for a given pair of target and input, we would need to derive what is the expression for the partial derivative of the negative log likelihood of observing some given target given some input with respect to any parameter theta in our model. And it actually takes a fairly simple expression that's very general. So that partial derivative would always be minus the sum over all the factors of the partial derivative with respect to my parameter of interest of the log factors. So over all the factors, I'm taking the sum of the partial derivative of each log factor with respect to my parameter, and I'm subtracting to that the expectation over the what could be the true label y. This is the expectation with respect to the model of, again, the sum of the partial derivative of the log factors. So here we have a difference between what a gradient of what is based on what is observed minus a gradient based on what the model thinks. It's conditioned on the input, but we're doing an expectation over what the model thinks is most likely. And if you think about this expression, what it's trying to do is that it's trying to make the log factor larger for the values of y that are in the training set. And in expectation, it's trying to make the log factors smaller in expectation for essentially every value of y based on what the model currently thinks, the way it assigns probability to other values of y. So if the model becomes very good, then p of y given xt is going to be peaked, assign a very high probability to the true target yt, and then 0 to everything else, in which case these two terms would cancel out, and otherwise training would proceed until we have converged to a conditional distribution that's very close to assigns essentially perfect probability to the true answer. Now, in this expression, the main problem is computing the expectation over y here. So this expectation here of this whole expression. So for one thing, it's an expectation over all values for all the elements in the y vector. But usually, since each of the log factors will only involve maybe a pair or triplet or just a subset of the y's, then usually this expectation reduces to an expectation over just a subset of the variables. So, for instance, in the linear chain conditional random field, we saw that essentially these expectations were only over either a single yk variable or a pair yk variable. So often it's only going to involve a few of these yk variables. That being said, computing the conditional distribution over these subset of y variables, if the graph is not a tree or a chain, that's still intractable. We have to approximate that conditional distribution. And what we can use is the loopy variant of belief propagation to approximate that conditional distribution. So it's just a reminder of how we can use the log messages as computed by belief propagation. So we're running belief propagation, usually in log space. We run it where we iterate over all the messages that are being passed between factors and variables, and vice versa. And we go over these messages several times until the value of the messages doesn't change. And once this has converged, then we can compute, for instance, the marginal probability over just a single y given x as just the exponential of the log factor that only involves yk plus the sum for all the other factors of the log messages that comes from them. And so this way we have a way of approximating, in this case, the marginal distribution, but we can generalize this formula to any subset of yks. So I won't go more into the details of this. This is just give you a head start if you want to go look at the literature for how to perform and train general conditional random field models using loopy belief propagation.